Hello, so in today's video, we're going to look at solving equations with modulus signs. So, for example, these for examples here, we're going to do these for examples today in this video. And the way we're going to do this is we're going to use a graphical method to do this. We're going to use graph sketching. So we're going to use the graphical method to solve these. So in other words, we're going to sketch the graphs, the necessary graphs that will help us with these problems here. You can also, I mean, with these two here especially, you can also use an algebraic method using the fact that when you square the modulus of a number, this is just the same as the number squared. You can actually just use that fact by squaring this and that, and then doing some algebra to get the solution from there. I'm just not going to do this because sometimes when you do this method of algebraic squaring, you may get extra solutions which actually don't correspond to your initial value, your initial problem, which means that you've got to substitute in your answer at the end to check whether your solutions that you got do work for the original equation. So I'm not going to use this algebraic trick here today in this video, but it's just worth bearing in mind that yes, when you square the modulus of a number, that's the same as the modulus squared, and that's because the modulus of a number squared is literally just the square of the number itself. So yeah, we're going to use a graphical method to solve all of these problems here today. So the first example, question number 1. So we want to solve the modulus of x plus 4 equals the modulus of 3 minus x. So the way we're going to do this is we're going to use this graphical method. So we're going to sketch the left-hand side equals y, and the right-hand side equals y, like I've written down here. So, okay, we know how to sketch these because we've done this in previous videos. So we know that we can sketch y equals the modulus of x plus 4. Again, it's just like a V shape. So it's basically the graph y equals x plus 4. But as soon as we touch the x-axis, so gradient of 1, y-intercept of 4. So as soon as we touch the x-axis there at minus 4, we're just going to reflect ourselves up like that. So that's our first graph. So y equals modulus of x plus 4. And then our second one, y equals modulus of 3 minus x. So it's the same as the 3 minus x graph, y equals 3 minus x. So something like this. But as soon as we touch the x-axis at x equals 3, and we know that that's going to be 3 there because when we sub in 3 into this expression there, we get 0. So we get a y value of 0. So we know that we're going to reflect ourselves upwards like that. And the key thing to note is that the gradient here and the gradient there is the same, and the gradient here and the gradient here is the same because of the number, the coefficients in front of our x's there. So that's just worth bearing in mind here. Okay, so now then, how do we solve this? Well, let's look at our points of intersection. So we've got a point of intersection here. So what are the lines in which this point of intersection arises from? So it arises from this line, which I'm going to do in blue, this straight line. And it arises from this other line, which I'll do in blue as well. So it arises from the line y equals, so minus, so 3 minus x, the line y equals 3 minus x. So this there, and also the line y equals positive x plus 4. So the positive version of this. So when this number is greater than 0, obviously y is equal to x plus 4. So that's where I've got this from. And when 3 minus x is less than 0, so in other words, when x is so 3 minus x is less than 0. So in other words, when x is greater than 3, we get this graph here. So essentially, where these 2 points intersect will be our solution. So if we just make 3 minus x equal to x plus 4, and then we solve this, we get minus 1 is equal to 2x. So therefore, that means that x is equal to minus half. So this point of intersection here is going to be negative 1/2, and that would solve our problem. So yeah, so the solution is going to be x is negative half, as we can see from the graph there. And again, that's because so in the left-hand side case, when x plus 4 is bigger than 0, the graph here is y equals x plus 4. And in this case, when 3 minus x is less than 0, so greater than 0, my bad. So when this is greater than 0, that means that x is less than 3. So I should have said before that x is less than 3. So that's why we get this these two graphs intersecting at this point there, and that's why we get that solution there. Okay, so that's the first example. Let's go to the next one. So again, similar thing, we're going to sketch both of the graphs. So first of all, the left-hand side graph, so y equals the modulus of 3x minus 5. So it's just the same as the 3x minus 5 graph until we hit this point there. And if we just set y equal to 0, we can see that this is going to be the coordinate where we intersect there. So we know that that will be, apologies, I made a mistake there, should be the other side here. So yeah, we've got the 3x minus 5 graph, which is going to be something like that, but obviously we're not allowed to go below the x-axis because of the modulus signs, so it's something like this. So this point of intersection there will be 5/3. We can see that because if we make this equal to 0 and rearrange for x, we get 5/3, and then it's just going to reflect itself up there. And then when x is 0, we can see that this point of intersection there will be 5. So yeah, we get a graph like that. And then how about this second one? So y equals modulus of 2x. So it's just going to be the y equals 2x graph, but the positive V shape reflected upwards. So I guess the key thing to note with this one is that the gradient here is lower, has a lower magnitude than the gradient there. So actually what will happen is instead of going like this and then these two curves here, these two lines diverging, they're actually going to converge. So something like this will happen where they're going to converge and they will actually intersect again. So let me try and draw that line straighter. So something like that. And obviously, yeah, the V shape reflected up like this. So this would be our line y equals modulus of 2x. And this up here would be our line y equals modulus of 3x minus 5. Okay, so that's our two graphs. So where do they intersect? So we've got 2 points of intersection here. So there and there. So let's think about the first point of intersection. So this is when the modulus of 2x graph intersects with the left-hand part of the modulus of 3x minus 5 graph. So in other words, I call this number 1 there, and I call this number 2. So for number 1, this is the intersection. So intersection of y equals 2x, because this is the positive part of this graph in this positive, but when x is positive. And also the graph y equals, so negative of 3x minus 5, because this is the negative part of this modulus of 3x minus 5 graph. This is the negative half of that graph, of the left-hand side of that graph. So in other words, minus 3x plus 5. So where these two lines intersect will be our intersection point. So we got 2x is equal to minus 3x plus 5. If we just rearrange this to x, we get 5x equals 5. So therefore, x equals 1. So we get one solution at x equals 1, and that's our solution there. Okay, great. So we got that one. How about the other point of intersection, this number 2? So if we look at number 2, this is the intersection. So intersection of, so y equals 2x again, because again, this is the 2x line there, and this is the positive half of the modulus of 2x line, which is just y equals 2x, and also the positive half, so this positive half of our first graph, the y equals 3x minus 5 graph, so actually just y equals 3x minus 5 without the modulus sign this time, because again, we're in the positive half of this y equals modulus 3x minus 5 graph. Okay, so the points where they intersect, again, we're just going to set them equal to each other. So 2 equals 3x minus 5. Rearrange this for x, we get x equals 5 just by taking away 2x on both sides, adding the 5 to both sides, we get x equals 5. So this point of intersection up there is going to be 5. And so we get our two solutions. So we get x equals 1 or x equals 5. And they would solve this equation there. Okay, fantastic. Great. So that's that one. How about this one? So this time, again, we're going to sketch the graphs. We're going to sketch the left-hand side graph and also the right-hand side graph. So yeah, we've got y equals modulus of 3 minus 2x, all inside the modulus sign. So again, this is just the same as the y equals 3 minus 2x graph for the positive bit, and then reflected at x equals 3/2. Again, when we set this equal to 0, we can see that x equal to 3/2 when this equals 0. So we've got 3/2 there, and it's going to be a negative gradient, an intersection point at 3, as we can see when we set x equal to 0, we get 3 as our y-intercept there, and it's going to reflect itself like that again. Okay, great. So that's that. And again, the magnitude of this gradient is 2 because we can see that there. And the same with this one. However, this time there's a bit of a transformation going on. So we've got y equals 3 minus modulus of 2x. Okay, so we know the modulus of 2x looks something like this because we did this on the previous page. Now, if we put the minus sign in front of it here, what does that do? Well, we know that just reflects it upside down. And that's because when you take the negative of a number, obviously you make it negative. So it just flips the graph like that. And then we're adding 3. Okay, so we're adding 3 to the graph. So that means we're shifting this this downwards V-shaped graph up by 3. So we're basically shifting it up to here. And I'm going to do this in blue. So we're shifting it up to this point here. Now, again, so the absolute value, the magnitude of the gradients here are the same. So actually the gradients here are exactly the same. So we get something like this in this case. Okay, so I'm going to rub out these dotted lines here. This is just working out, which you can do in pencil in the exam. So yeah, we've got the modulus. So y equals 3 minus modulus of 2x there. And we've got y equals modulus of 3 minus 2x there. So, okay, so where are the intersection points? Where are our solutions? Well, this is obviously x equals 0 there. We've just worked out that this is x equals 0 over 2 there just by setting this equal to 0. And we can see that they overlap between 0 and 3 over 2. So we've actually got a set of solutions. So the solutions will satisfy. So solutions satisfy. Well, x is between 0, so 0, and also 3 over 2. So that would be our solution set, our set of solutions. Any x value between 0 and 3 over 2 inclusive, just because we're including the 3 over 2 and the 0 there within our graphs. Any of those values would solve this this equation up there. Okay, so that's that one. And then this one here is a little, well, similar but a little bit different. So we got 2 and then modulus of x plus 1 plus 3 equals a times x. And it has solutions. We've got to find the set of a values such that the solutions here exist. Okay, what I'm going to actually do with this one is just rearrange it. So I'm going to write it like this instead. So 2 times modulus of x plus 1 is equal to ax minus 3. Okay, so let's sketch in the left-hand side with this one. So y equals modulus of 2x plus 1. So, okay, if we sketch this in, remember, we've got two cases. If x plus 1 is positive, x plus 1 is greater than 0, well, that means that the modulus of x plus 1 is equal to x plus 1. So we've got the line y equals x plus 1. But when x plus 1 is less than 0, remember, that means the modulus is actually equal to the negative of that. So that means that the modulus of x plus 1 equals negative x plus 1. So we've got the graph y equals negative x, negative 1. Let me just make this smaller. Sorry, 1 second. There we go, right. Okay, so then we can just sketch these graphs in. So x plus 1, y-intercept there, something like this, gradient of 1. It's going to intersect there at -1. And then it's going to reflect itself upwards like that. So that's our oh, sorry, my bad, this is a mistake, sorry for that. This should be 2 because, yeah, sorry, we're multiplying that by 2 there. So actually, really, I should be saying I should be putting the let me rub this out, put the 2 there times by x plus 1. And with this one, similar story, we're going to do -2 times by x plus 1. So yeah, actually, when we expand the brackets, we can see that we get 2x plus 2 in the positive half and -2x minus 2 in the negative half. So this is certainly a 2 there, and this is certainly a -2 there. So apologies for that. Actually, no, sorry, that's a -1. Sorry, apologies again. That's -1 there, just because when you set y equal to 0, you get x is -1 there. Okay, so that's our first graph. Now we've got this this other graph, this this ax minus 3 graph. Let me make a note of this here, this right-hand side graph. So so y equals ax minus 3. Okay, so it's going to be it's going to have a y-intercept of -3. We can see that, and it could be, well, let's think about it. It could be a line like this, could be a line like that, could be a line like that, like this. Could be any of these type of lines. Which lines will give us solutions? Well, let's think about it. Here we've got a gradient of 2. So this this positive half, this right-hand side half of this modulus of 2 times modulus of x plus 1 graph, we've got a gradient of 2. Now, if we had an a value of 2 here, so y equals 2x minus 3. Now, this would just be the same gradient, and so it'd be a parallel line. So there would be no intersection point. So we know straight away that a can't be 2. But what if a is a little bit bigger than 2? Well, if a is a little bit bigger than 2, eventually there's going to be an intersection point somewhere up there, eventually. So what we know then is we can see that a must be greater than 2, because if a is greater than 2, then we're eventually going to intersect, and yeah, the bigger the a value, the steeper the line. So as a goes to infinity, I mean, you'll never exactly get the straight vertical line on the on the y-axis there, just because technically you'll never get to infinity, because infinity is not a number. But the bigger you go, the straighter the line will get, the more vertical, I should say, the line will get. Okay, so we've got that bit of the solution. How about the negative bit? Okay, so what if we've got a line like this? Well, we're not going to intersect, so we're going to get no solutions. So then the question becomes, okay, so what happens if we have a gradient such that we eventually, sorry, let me try and draw this a bit better, such that we eventually have an intersection point there? When's that solution going to be? Well, let's think about this. Let's think about the gradient of a, so the value of a, the gradient, which is going to give us an intersection point at this corner here, this point here, this non-smooth point. So we're going to get an intersection point here, and then for gradients with a magnitude a little bit less, we're not going to get we will get intersection points like there and there and there. But obviously, if we've got a gradient of -2 for a, then that's going to be parallel to this line here, because remember, the gradient of this negative half of the 2 times modulus x plus 1 graph is -2. So actually, we can see again that the gradient, the a value cannot be -2, because otherwise we get a parallel line. However, if the gradient is less than -2, so a little bit, so the magnitude being bigger, we're eventually going to intersect this part of the graph. So actually, we can see also that we need, so we can see that a must be a little bit smaller. Sorry, well, it must be smaller than -2, and actually equal to, actually, sorry, not equal to -2, because obviously we can't have a parallel gradient. So it must be less than -2. So it could be -3, -4, -5, because then we'll get our intersection points here and here. So okay, so we know that, and yeah, so that would actually tell us the solution. That gives us our solution. So we can see from the graph that a must be bigger than 2 and a must be less than 2. Sorry, less than -2. So they would be the two sets of values in which this equation this equation would work. So for example, an a value of 1, we're not going to get any intersection points. A gradient of 1, we're not going to intersect. A gradient of -1, again, we're not going to intersect. And gradients of 2 and -2, we're not going to intersect. But gradients bigger than 2, so an a value bigger than 2 and an a value less than 2, we are going to intersect with this graph, and so there will be solutions. So the solution, so the set of solutions will be this. So yeah, so in other words, the set of a values, so set of a values in the real numbers, sorry, let me write this down here. So set of a in the real numbers such that a is less than -2, or a is greater than 2. So that would be our set of solutions there. So yeah, that concludes today's video.